at home?
Yes, I am now at home, not in the office.
Home.
Yes.
Okay. Yeah.
I was actually in a meeting. Then I came just before 5 minutes. I arrived home, and I was looking forward to see you and to see this nice lecture.
Okay. Yeah. So Dr. Jing, tell me that you discuss a lot on the cooperation between our two regional centers.
I would like to. Yes, I would like to organize a special Zoom meeting with your actually Highness to discuss actually in more detail, because there are many ideas which we can actually just start this kind of cooperation, which will help us, because our universities here, they are looking for them, and also your esteemed pioneering and also working very much hard for the sake of establishing and publishing the science all over the world. So I will actually organize with Professor Xiang.
Yeah.
And he will just see what's the reasonable date for the next special Zoom meeting with you, and let's actually put the agenda. I will send the agenda, and you just amend whatever you like, and tell me exactly what exact time we can start. So, Ibrahim, are you ready?
Yeah.
Dr. Ibrahim.
Now the signal is not very good, so I can't hear you clearly.
Okay. Yes, I am Dr. Ibrahim and also Professor Yang. If you are hearing us, before we will start, you would like to take the, you see the instruction and guidance from Professor Wang about this cooperation, which we have already started with the Regional Center behind University. Of course, Dr. Wang, do you hear me now? Dr.
Yes,
Wang?
yeah, I can hear.
Yes,
yeah.
Dr. Wang, please, we would like to take a guidance from you and start this important lecture presentation. So please, it's your floor now to hear from you.
Okay, so I will share my screen.
Yeah. I think today.
I would like to repeat. We would like Mr. Wing to give a guidance, you see, and recommendation about the future and what we are doing, cooperation between each other.
Okay.
Please, Dr. Wing, if you would like, it's your floor.
Yeah, okay. So I think after we can get a draft of MOU, then we can go to more detail and organize another Zoom meeting. So today we are just give the time for the lecture, I think.
Very good. Very good. That's fine. And you are welcome again. And please, Dr. Ibrahim, trouble.
Yang, please.
Okay, I'm ready.
Okay. Professor Yang, now you have the floor.
Yes, okay, I'm ready.
Okay.
Yeah.
It's your floor, please.
Yeah.
Mr. Yang?
Yes.
Yes, please. You can start. Thank you.
You
very
can
much.
share your screen, or you have.
Okay, please. Please, Ibrahimi, please.
Yeah. You are co-host. Please, you can share your screen.
Yes.
Okay.
Now it's okay? Yes.
Yeah.
Okay, okay. Now working. It's working.
Okay. So, shall we start?
Yes, please.
Okay. In the last class, we discussed that the GNSS reflections could be used for the remote sensing applications. This time, we will talk what the applications are. Actually, navigation satellites signals reflected of the surface have geometrical objects and physical objects, which are used for different application scenarios. So this is a basic principle introduced in last class. And the observables, such as the primary delay map or Doppler map, and the delay Doppler two-dimensional map will be used for these different applications. So from the Earth observation point of view, the Earth's surface could be classified into two different fields. One is ocean, the other one is land. So we will discuss the applications into these different scenarios. Before we enter into the applications, we will say the basic progress in this area. So the red flag, the first red flag, is marked in 1988. So at that time, the GPS system was started only around 10 years. So at that time, the scientists in Europe have looked the phenomena during their test near the sea. So they find the GNSS satellites could be configured into biostatic gyrometer for some potential applications. So after that, in 1991, the reflected signals were validated to be applied in the remote sensing. After that, Martin-Leroy-Monod from European Space Agency proposed the new concept, Paris. It is the first start for this GNSS reflectometry remote sensing applications. So Professor Martin-Leroy-Monod is a very important person in this area. Actually, China and Europe established one joint GNSS-R research group. The Professor Martin is the European coordinator, and myself is the Chinese side coordinator.
Very good.
So this joint research group was established in 2012. So the basic idea for this Paris is radar altimeters applications. Actually, the GNSS-R could have much higher temporal and spatial resolution than the traditional radar altimeters. So in 1995, the GPS was in full operation capability. 1 year later, the airborne test for the GPS reflections was validated to be used for the sea wind remote sensing applications. So this is another new application scenario in GNSS-R area. Since 1998, the interferometry concept was proposed based on the single antenna configuration mode. It is the new application scenario. It is because that the GNSS course network could be used for these GNSS-R applications. From 2005, the spaceborne GNSS-R entered into one new era as the UK DMC constellations launched. So after that, many spaceborne program was initiated in the whole world. It include the Chinese government. So in last year, Chinese company launched the new constellations, which includes 2 GNSS-R microsatellites called number 1 and number 2 Bufeng satellites. So for the spaceborne GNSS applications, CYGNSS from NASA and the Paris from ESA and GEOS ISS from Europe Union and GFZ are 3 typical milestone missions. So it is quite important for the GNSS-R global remote sensing applications. So then let's say what the remote sensing applications are. So for the GNSS-R, we can get the physical parameters such as the sea wind, the altimetry, the sea ice, the soil moisture, snow depths, and the significant view height. So GNSS-R has many applications similar as GNSS. We can see that its applications are only limited by our imagination. As the Earth's environment observation, we can classify it into the following 3 areas, roughly. First one is the ocean sensing. So the National Oceanic and Atmospheric Administration, NOAA, from United States, Hurricane Hunter research aircraft carrying on a GPS reflectometry instrument flew into Hurricane Michael of the South Carolina coast in October 2000. So the first GPS signals reflected from the sea surface inside tropical cyclones were analyzed, and the wind speed results were obtained at that time. So another application is UK DMC carried a GPS reflectometry experiment as a secondary payload, from which geophysical parameters of the Earth's surface were successfully inferred. That is, the sea surface roughness parameters was obtained. So the good altimetry accuracy results have been obtained in very calm sea states with GPS reflected signals. Of course, for some leak test or the is-to-Rari test gives some good results. So currently, the GPS reflected signals from the ocean surface can be used to make altimetric sea surface height measurements with the achievable accuracy. So an active topic research was there. So good examples of ocean roughness and wind sensing using GPS signals have been discussed and demonstrated in recent years. So for the hydrology sensing, the power level of GPS reflected signal from the land contains information about the soil moisture, the electrical constant, and the surface roughness, and even some possible vegetation cover of the reflected surface. So for the chromosphere mapping, it is focused on the sea ice and the snow dips, and some test on the snow water content. So based on the previous classification and the recent new application study, I will introduce these 6 typical applications. The first one is altimetry. So the GNSS-R altimetry is a popular topic and useful for the following topics. The first one is eddies and fronts. They are essential to understand ocean circulation on all space and time scales, but a large fraction of their kinetic energy is associated with spatial scales that cannot be resolved with a single radar altimeter, like the left picture. This is a traditional radar altimeter. So the mass scale variability is a key to understand large-scale circulation and climate variability through eddy transport of momentum interactions with the mean flow and meridional heat transport. So GNSS altimetry, with its relatively large number simultaneously measurements, can provide greater spatial and temporal resolution. Like the right picture, if one LEO satellites rise in the orbit, so there will have more than one trajectory underneath the satellite. So the second topic is on tsunamis. It is at open waters, have relatively small vertical signal, but very large horizontal pattern, corresponding to ocean waves of long periods and long wavelengths. So its detection and warning must be as quick as possible, preferably 15 to 25 meters after its origin. So the synoptic view capabilities of the GNSS-R system might help detecting them timely. So the third one is geotropic velocities and gravity anomalies. So they are estimated based on the measurements of the surface slope. Radar altimeters can measure surface slopes in only one direction along track, except at widely time-spaced track crossover points. With GNSS-R altimetry, the slope measurements could be done along the path of the multiple simultaneously specular points on the surface. So similar as the last applications. The next one is the tides. In particular high-order tidal components, the tides might be better identified than in standard radar altimeter because of the non-repeating nature of the GNSS concept. Another possible advantages of the GNSS-R altimetry could be better sampling of internal tides of wavelengths below about 100 kilometers. So these tides play an important role in large-scale circulation and vertical mixing in the deep ocean. So the last one is the physical, chemical, biological interactions. So these interactions mostly occur at scales not resolved with radar altimeters. One of the more important of these interactions is the ocean's connection to the carbon cycle, which is crucial to understanding long-term climate changing. So to do the GNSS-R altimetry, some factors we must consider. Firstly is the geometry components of the slant delay. From this graph, we can see the GNSS-R can measure the electromagnetic slant delay between the transmitter and the receiver. So after the signals rebounds of the sea surface, rho, this electromagnetic delay contains a geometrical component, rho GO, and the components from the atmosphere delay, including the inotropic and the tropospheric. And this rho ins means the delay from the instruments. That is hardware a delay. The N means the noise. So this is the basic idea of the geometrical components of the slant delay. So assuming it's possible to separate, correct, to reduce the non-geometric components of the slant delay. So a measure of the vertical location of this reflected surface can then be extracted from its geometric contribution. So this vertical location, usually known as the altimetric solution, corresponds to an average or statistical central tendency of the instantaneously surface height across the footprint. Like this is the zoom in of this point. So it needs to be distinguished from the mean sea level at that same location, which is the measure of the average height after a long time series. That means this is the average value from the signals. So the non-geometrical terms include the carrier height and the effects from the atmosphere, and some factors from the possible frequency dependent values. So the total delay suffered by the microwave GNSS signals is affected by the atmosphere. The ionospheric delay and the tropospheric delay could be reduced by the dual frequency techniques and some tropospheric modeling to reduce its effects on the slant delay measurements. But for different altitudes of the GNSS-R receiver equipped, the atmosphere path will be different. For example, for the space-based receivers above or on top of the ionosphere, the ionospheric effect comes from two different regions of the ionospheric layers. So the regions are at large distances. for the low altitude receivers, the ionosphere is crossed only once, and the troposphere may be crossed twice. So for the different application scenarios, we will use different modeling and different calculation equations to calculate the delay. So for the frequency dependent effects, dual frequency is a good technique to cancel the ionospheric effects. Even though the surface roughness will also affect the dual frequency modeling error mitigation effects. So we must consider these additional and potential errors. So in order to solve the altimetric problem, accurate knowledge of the position of both transmitter and the receiver antenna's phase center are required. So here we assume that all of the accurate position will be known from the existing high accuracy orbit ephemeris. So after that, we assume this S0 means the specular point and its surrounding areas, like this curve. So then we know the function f to calculate this rho. In addition, it's possible to correct for vertical displacements of this point of the prior surface around Q. How to do that? The linearization around this point is a good solution to cancel the vertical displacement of this point, Q. So if the GNSS receiver is equipped in the low altitude receivers, like this graph, the receiver was equipped on the aircraft. So then we can use these equations to calculate H. So this is the basic idea to calculate this H. Of course, H here is not the ocean height, but the vertical distance between the surface, this surface, and the receiver. So then, if we know the position in high accuracy of the carrier, then we can use these equations to get the height of the ocean. So how to get the accurate H? So this graph shows us the GNSS satellite signals includes the carrier and code. So then the group delay from code and the carrier phase from carrier, both of them could be used to calculate H. So how to do? Of course, the different parameters will give us different accuracy for the altimetry. So let's have a look how to calculate these two parameters. So this is the calculation methodology for the group delay altimetry. So this autocorrelation function, like the CA code autocorrelation function. So if the reflected surface is not the mirror-like, so the autocorrelation function will be like this. So from this graph, we have three typical points to consider. So the first one is the nominal delay, is the black dashed line. So second one is the specular delay with model, this blue line. So the red line is from real data. So if the surface reflected is mirror-like, so its roughness is less, then we could use the maximum wave delay to calculate H. So if not, then we can use the maximum derivative delay to calculate. So here is the three different methodologies. So we use the different delta rule to compensate the delay calculation. So this is the peak delay. This is the model fitting. This is the peak derivative. So here, two examples of waveforms derivative made with real data are displayed in the right figure. So this one is the derivative of the PIT waveform and the derivative of the CA waveform. So this is the two typical application mode. So we discussed in the last class. So they correspond to the derivatives of the waveforms shown in left figure. So for the PIT waveform has steep slope than the CA waveform, like this. So of course, the different group delay resolution from the different techniques will give us different accuracy on the altimetry. So another key factor besides the roughness of surface is the sparkle noise. So the determination of the specular range should be done on a sufficiently integrated waveform to minimize the effects of the sparkle. So last time I remembered I talked the sparkle noise has a specific distribution in the frequency. In highly dynamic scenarios like space or air-based receivers, and whenever a prior estimation of the nominal delay by the receiver or some of its parameters are not updated as fast as the dynamic changes of the geometric conditions, a realignment of the waveforms must be conducted before its integration. So this realignment uses refined post priori estimates of the involved parameters. We called this process retracking, like this graph. So if we do not do the retracking, then we will get the red line like this at the bottom of the graph. So if we realign the waveforms, that means the retract integrated waveform will like this. So of course, this one will provide us much more accurate information. So this is the basic idea, retracking. So this table shows us some experiment results performed by the scientists from all over the world. For example, the code here, CA and P, means CA code or CA and P code are used. So the PIT means the PIT technique used. So the static aircraft and the LEO means the different altitude equipment in the of the receiver. And the S means only one satellite we used. The M means M satellites are used at the same time. So in summary, the precision obtained when the surface roughness and dynamical conditions permit to acquire phase delay observation is of the order of 2 centimeters. In integration times of 1 second, these results have been reported from different experimental sites using different processing techniques and the receiver altitudes from a few meters to LEO altitudes, that is a few hundreds of kilometers. So the group delay observables have to be used in most of the ocean GNSS-R altimetric measurements. So different experiments using different instrumental setups, processing techniques, and even receiver altitudes up to 3 kilometers for airplane applications, resulted in 1 second integration time, 1 GNSS satellite, and the CA group delay altimetric precision of the order of 1 meter. Of course, most of these experiments have been conducted with avionic antennas, that is, antennas with low gain hemispherical patterns. For the multiple satellites approaches, higher integration time strategies and considerations about systematic errors that could be corrected improve significantly the precision. So the use of wide bandwidth codes, such as P code, Y code, or the Paris interferometric technique, PIT, which makes use of the whole bandwidth with no need to model the codes, also improve the performance. So 5 centimeters precision in PY airborne multiple satellites altimetry. So 7.5 centimeters precision for static PIT in 1 second and 1 GNSS satellite. So the airborne test result showed that the PIT technique has 13 centimeters precision with a 20-second integration time and 1 satellite. So this is the cases study. For example, this is a dual antenna mode. So this is a code replica mode. will output 2 waveforms. So this is the PIP mode will give us 1 waveform. So this is the basic data processing flow for these techniques. So this is the single antenna mode, which is called GNSS-R IR. GNSS-R IR, interferometric reflectometry. So the principle for this kind of application mode is the interferometry signal will have different amplitude and frequency model based on the different receiver height. So this is the experiment we have performed in China, Dongying City. This is a coastal receiver installation. We test in October in 2017. So after we collect this raw data, we do the spectral estimation. After that, we estimate the tide information to compare with the existing site data from the observatory administration. So this picture is from Denmark's Technic University. So the similar configuration with ours. So this is the first application, altimetry. So now let's see the second one, the ocean surface roughness. Actually, the sea wind increasing the wave's height and length is, of course, the wind transfer the energy from the air to the water. So, however, as the wind blows, it increasing the wave's height and length in different stages. So, for example, this one in a fixed wind speed, the wave h omega has different for the different sea state. So what does it mean? So when the wind starts blow, the wave will be higher over the time. But when the wind speed matches the wave's heat, the wave's crest, then the sea state is named developed sea. So it's a equilibrium status. So then after that, the wave will be decaying, after the wind passed by. So based on this idea, the inversion modeling will have such kind of parameters to consider these factors. So the L-band radiometric measurements of the surface salinity have a major systematic effect induced by the surface roughness. So the sea roughness parameters from the L-band GNSS-R could also be used for the salinity measurements from the radio metric instruments. So this is the cyclone missions from NASA, Michigan universities. You can get much more information from these 3 websites. So for example, we can get the live track for the wind from this link address. So let's try to see whether we can browse it. I don't know whether the website is okay to look the track. Yes, so this is the real-time strategy from the website. So every day. So it's quite good. You can see more information from the website. So the roughness measurement can be given as statistical properties of its slopes. So the slope's probability density function, or its actual numerical realizations of the elevation of the surface as a fine grid on the XY plane. In ocean applications, both statistical characterization and numerical surface realizations can be obtained from the ocean waves spectrum. So the spectrum will give us the distribution of the ocean wave energy density with respect to the wave's temporal or spatial frequencies. Like this is the wave number K, this is the frequency omega. So the wave's spatial frequency and the wave number could be transferred each other, could be converted into each other. And it could make use of a particular dispersion relation between the K and the omega. So for deep waters, depths larger than half wave's wavelength, the dispersion is related to the gravity acceleration. So the spectra can be measured for a particular site and epoch, or it can also be modeled as functions of a given set of parameters. So typical parameters that relate to the sea state conditions are the wind and the significant wave height. So other parameters that can affect the spectrum are the fetch, which is the length of water over which the wind has blown, and the stage of development of the sea. So the waves grow higher in altitude and longer in period as the wind blows longer or over larger areas. So this is the 3 different stages of the sea: developing, fully developed, and the decaying phase. I explained in previous slide. So we have 3 typical frequency spectrum. First one is the PM. The PM is simple wave spectrum empirically obtained from the measurement in North Atlantic in 1964, and it was revised in 2003. The second spectrum is named GNSS-R. It is a well-accepted long-wave spectrum. After experimental campaigns in the North Sea in 1973, it is formulated as a modification of the PM spectrum, and it includes limited fetch conditions. So the third one is alpha Heli. It is a directional spectrum suggested by alpha Heli in 1997. It is widely used in the GNSS-R community. It is a full wave number spectrum to properly describe long and short waves. So both fetch and wave age, that is the stage of development of the sea, are included as input parameters. So we can see the different spectrum curves between the PM and the alpha Heli. So from this area is more or less the same, but in the right side of the two curves, it has a bit difference. So another difference is on the wind speed. So for the PM model, considered the speed of wind at around 20 meters altitude. Instead, the GNSS-R model considered the wind speed at 10 meters altitude. Of course, for the alpha Heli, the same altitude as the GNSS-R model. So besides the waves generated by the blowing wind, the surface might present waves from distant or past storms, what is called the swell. So they typically present regular waves of relatively long wavelength. So the reason that long waves travel faster than the short ones is keeping from the storm. So typical swell wavelengths are of the order of a few hundreds of meters, with significant wave height of a few meters. So there are no general rules to link swell wavelengths and SWH. So a possible way to obtain a spectra of given peak wavelength, lambda p, and given SWH is to play with a simple spectral model, such as a PM model, setting the equations between the Kp and the lambda p. So if we assume the linearity of the system, then the wind-driven spectrum can be added to the swell spectrum to obtain the total surface spectrum like this equation. So the surface slopes probability is the important parameters in the biostatic scattering coefficient. Such probability is usually a function of the mean of the square slopes, MSS. The MSS can be extracted from the slopes spectrum using these equations. So the MSS equals 2 multiply the sigma slopes square. It's important to highlight that these equations give the statistics of the slopes accounting for all the waves scales. However, GNSS L-band signals have electromagnetic wavelengths of the order of 20 centimeters, and they are in principle insensitive to roughness scales smaller than this wavelength. So then we have the upper bound of the integral like this. So the most used distributions are the ocean in isotropic cases, the 2D bivariate normal distribution for anisotropic scenarios, or 2D Grama-Collier distribution for higher order effects. So this 2D bivariate normal distribution consists the up-down wind direction and crosswind direction, respectively. But it does not account for the up-down wind asymmetries. So the Graham-Collier distribution was suggested in 1954 by Cox and Monk after the analysis of photographic observations of the sun glitter. So this distribution accounts for skewness and pickedness in the statistics of the slopes. So this numerical calculation is for wind speed 8 meters per second along the x-axis. So the left one means the downwind direction points towards positive x, like this one. So for the right graph, the downwind direction points towards negative x. So we can say there is a asymmetry curves. So for studies of phase-related behavior of the scattering, it might be interesting to model the surface as realistic numerical realizations of its fine topography. So some polarization issues not well solved by the KGO approach might also require Monte Carlo-like simulations based on scattering integrals of realistic surfaces. So the realizations of the surface elevation can be obtained from inverse Fourier transform like this of the squared root of the wave number spectra. This one. So of course, in this equation, a random arbitrary phase is added to each wave number, like the phi. So because of the sparkle noise, which includes noise proportional to the power, the scattering of one single realization is not significant. So, but larger ensembles are required. So that is means the integration will light a longer time. So the for these two pictures, the wave age is fully developed, 6 meters per second along the x directions. So this is a swell from the storms, and the SWH. The PM spectrum was added for the 50 degrees direction. So XY axis annotations are given in meters. So we can see the different. So if we establish the foundation of all these equations, the slopes, the slant delay, and the probability. So the last question is on the retrieval approaches. So if we get the wave form from both the PIT or code replica technique, so there are some GNSS-R ocean surface roughness inversion techniques applied so far. So mostly to extract surface winds and MSS. So in particular, some approaches extract the wind speed, some others wind vector, including wind speed and wind direction, and the isotropic MSS, the 2D MSS, and the discrete and non-parameterized slopes PDF. So the DM fit is one of the popular technique for this application. So this is a DM fit. Of course, after renormalizing and realigning, so the delay will form, it could provide better performance. So the second value to calculate the parameters is DDM fit. So like this graph, this fit is performed on a delayed Doppler waveform. So in this way, the anisotropical information can be obtained from one single satellite observables. Of course, if we can acquire more than one satellite, then we can get more information on the wind or the slope. So this one is multiple satellite DM fit. And of course, we can get multiple satellite DDM fit. So for the DM waveform, the trailing edge, like this one, the trailing edge, could provide us the information on the wind speed and the wind direction. So from the two simulation results, we can say clearly the wind speed and the wind direction from the trailing edge. So as wind speed increases, the power peak decreases, but shifts towards larger delay. So and the trailing edge will be higher. So this is the typical information for different wind vector. So we have some other values or observables to calculate the roughness. For example, the spectrometer delay, DDM area or volume, and the coherence time. So for this coherence time, it is quite important for the significant wave height applications. So for this inversion techniques, we have applied in our own experiment, and we get some good results and published papers on this technique. So this is the wind vector calculation based on the DDM fit. So in our software GNSS-R receiver, we used this methodology for the poster processing. And this is our test result. Alpha Heli spectrum model was used, and the wind speed accuracy is around 1.4 meters per second. So, and the wind direction accuracy is around 20 degrees. So this is the test results from GFZ, sea wind and the rainfall. So the second case is on significant view height. So it the SWH is usually defined as 4 times the standard deviation of the surface elevation, or equivalently as 4 times of the square root of the zero order moment wave spectrum. So this is basic definition. So for our experiment, we found that the significant wave height has relationship with the width of the correlation function. So you can say different widths for this different waveform correspond to different SWH value. So we also test the Beidou system signals in 2017. The place is similar as the previous one in Shandong, Dongying. So we find there is a nonlinear function for the coherence time and SWH. So it's well fitted for this SWH. So the third case is on the multifunction test. So we used the complex correlation value to do the wind speed calculation and SWH at the same time, using the different empirical functions like this one. The U10 means the wind speed is above the sea surface 10 meters, like Jones-Wamp model and the Elf-Haley model used. So this is the SWH, its relationship with the tau R. Tau R means the correlation time. So for the Beidou system test, we collected the information from GEO satellites, PRN3. This place is on Shandong Weihai. The altitude of the antenna was put on 30 meters. So, and the LHCP antenna has a 40 degrees beam pointing to the sea surface, like this one, the behind one. So we compared the 2 months in situ data, get the accuracy of wind speed is about 1.87 meter per second. And the accuracy of SWH is 10 centimeters. We also demonstrate our GNSS receiver. So in 2015, we collect the data in the wharf of Shengli oil field in Shandong province. So in this one, around here. So we used this calculation equations to evaluate our result. And we used this into data collection for the wind speed. So we collect the direct signals from 4 different satellites, and the carrier and code phase of PRN3 is about 1 degree and 0.02 chips respectively. So the delay between the direct and reflected PRN3 signal is 42 meters, and the retrieved height is 30 meters, which is agreement with the height of the antenna. So the antenna is around 30 meters, right? So from this delay to this height, the equations is explained in the first slide. I remember in the altimetry, right? Two edge same elevation angle, more or less. So the amplitude distribution of the correlation function of complex correlation values follows the Gaussian function, like the left one. So the correlation time has inverse proportional relationship with wind speed, the wind speed and the correlation time. The IMSE and correlation coefficient between retrieved and in-situ wind speed is about 1.78 meter per second, and the correlation coefficient is around 0.9. So the fourth case is about the airborne test. In 2016, we performed the airborne experiment in Yantai, Shandong province. This is a flight path. So many times, many repeat times. So then we get the flight height and the velocity around 3,000 meters and 55 meters per second. So this is the visible satellites during the flight. So we used the different satellites to get the height information. So of course, different satellites will give us different height information. So the difference is about 200 meters. So the retrieved heights from different satellites are obviously different. So of course, we must make them consistent with the real value. So for the wind speed, a similar phenomenon, different PRN satellite will give us different wind speed value. So this value was obtained through the ZV model. So the fifth case is on the typhoon test. So we performed the spaceborne GNSS-R typhoon detection experiment. The date was from TDS and the NCEP reanalysis data. So we think the GNSS-R can find the location of the typhoon start and its travel path. So for example, the travel path, this is the this circle is the GNSS-R point, specular point or reflected area. So this is some wind speed comparison. So this is the relationship between the GNSS-R wind speed and the wind speed from NCEP observables. So for the typhoon test, we performed ground-based experiment. So in 2013, we make this experiment together with our European operation partners in Guangdong, Shenzhen. So this place was located in Xichong meteorological station. So we used geo satellites from Beidou. At that time, the European equipment was also put there to collect the data. In 2013, as the Galileo system cannot cover the Chinese area, so the European equipment collect the GPS data for comparison with us. So this is the number 9 typhoon in 2013. We detect this typhoon information based on the GEO number 4 satellites from Beidou system. So this is the number 4 Beidou satellite, GEO satellites. It's a correlation in time over the Beijing time. So the x-axis is the Beijing time. So the y-axis is the correlation time. So this is the direct signals in blue and the reflected signals in red in some time epoch. So we do the data processing based on our model, empirical model. This is the curve like this, U10, A, tau W. Tau W means the y's of the correlation function. B is the times plus K. So the mean error wind speed is about 1.6 meter per second. So this is the best results for our test. So this is the travel path of the typhoon. So up to now, we built 7 coastal GNSS-R stations along our China Sea. But some equipment was damaged by the typhoon. Some works well now. So in Zhejiang province, we put 3 stations here. Now only 1 work well. The other 2 was damaged by the typhoon. So up to now, we talked about the ocean remote sensing, which is related to the altimetry, firstly, and secondly on the sea roughness. Based on the sea roughness, we could calculate the wind speed. Of course, sometimes the wind direction are also calculated from the defined observables. So for the land applications, soil moisture is quite important. The soil moisture content is one of the important land parameters in hydrology, climatology, and agriculture vegetation, which provides useful information for energy balance and crop yield expectation, and plays an important role in the interaction between continental surfaces and the atmosphere. So that means the water recycle is important based on some information from the soil water content. So generally speaking, the microwave remote sensing has advantages with all weather detection, day-night ability, and penetration through a medium. So in the last class, I briefly introduced the remote sensing conventional techniques. So microwave is quite good and better than some optical remote sensing technique because of the day-night ability. So the wavelength of microwave electromagnetic is between 1 and 100 centimeters. The commonly used band is X, K, C, S, and L. So GNSS signals is L-band signals. The wavelength is about 20 centimeters. So the penetration through the soil is about 10 centimeters. So the real part of the dielectrical constant of the water is about 80, while the dry soil is almost 3.5. So this is the basic principle for the GNSS-R to calculate the soil moisture. So when the soil is wetter, it is the increase of the dielectrical constant and the decrease of the emissivity or increase of reflectivity. So then the basic reason for microwave soil moisture detection is the larger dielectric constant differences between the water and dry soil. So for the soil moisture calculation method, there is some traditional. This is the probe. This is the satellite imaging. This is the radiometric methodology. For example, radiometers, monostatic radars, and the global soil moisture from SMOS and SMAP. So this is a very popular remote sensing satellite. So of course, GNSS-R is good and better than some conventional remote sensing techniques. I talked many times in the two classes. And the L-band, like 1.5 gigahertz and 1.2 gigahertz for the L1 and the L2. Of course, the L1 and L2 has different bandwidth, so which can provide us more accurate information through the bandwidth information itself. In addition, GNSS-R receiver can simultaneously receiving multiple satellite signals in the field of view. So this is also important for the soil moisture calculation. And GNSS-R receiver has self-positioning and self-timing capabilities with easily accessing geographic information network. So this is also important for the precision agriculture, for the smart agriculture. At the same time, the vegetation cover is one of the difficult problems that should be considered in soil moisture estimation, because the vegetation will affect the reflections through the from the soil. So meanwhile, GNSS-R with low cost, small power consumption, high spatial and temporal resolution, and some other advantages make it possible for vegetation parameters monitoring, such as vegetation biomass and vegetation growth condition monitoring. So it's quite useful. So this research topic has a similar configuration scenario like altimeter and sea surface roughness. Here, one specific technique named IPT, not PIT, we talk about PIT, right? But for the soil moisture, there is one new configuration mode called IPT, interference pattern technique. So this idea is from the ground-based semi-Gauss refractory experiment. So I will introduce more. So before that, the first one called quantitative relationship between the soil moisture and the received waveforms. So this one is an extension from ZV model, which is a typical modeling for the ocean remote sensing, right? So this ZV model was extended to soil moisture remote sensing applications. So I will introduce more detail the IPT because it's quite interesting. What is IPT? Like this one. We put one antenna here, but this antenna is not a circular polarization antenna. You know, in the previous applications, we used one antenna to detect the SAR for some applications, like the sea level, but that antenna is right circular polarization antenna. But here, we put one antenna with linear polarization. So this is the differences between this application and the previous one. So the direct and the reflected signals performed interference automatically at the antenna, right? So if we use the linear polarization antenna, then the components of the reflected signals will have two linear signals which composed of the circular polarization signals. So vertical polarization and the horizontal polarization signals. So these two figures present some simulation results at vertical and horizontal polarizations over land. So here, this is left figure is for vertical polarization. Here we can see the notch, notch amplitude, and the notch position. So these two values could be used for the soil moisture calculation. As a comparison, the H polarization has no obvious notch amplitude. So there is no obvious notch. So for this IPT technique, the vertical polarization antenna generally are used. Of course, some tests use the vertical polarization antenna and horizontal polarization antenna together, so which is a dual polarization antenna. So some test. So this is the semi-Gauss reflectometer test performed by the institute. So here we can say the PIN19 on at vertical polarization. This soil moisture is around 24%. So this one is from PIN15 at vertical polarization. The soil moisture is around 24 also. So this information was calculated for the notch position. So I think this one is quite interesting topic. So this is the soil moisture information from the probe. So it's around 24 to 26%. So the APT technique can get 24, right? 24.2, 24.5. So its accuracy is good. So to know what is the depth of GNSS signals can propagate it into the soil, the field test was performed in Beijing by my research group. We performed it about 3 months. So what's this idea? So we put 2 antennas on the surface of the soil. This is surface of the soil. Then we cover one of the 2 antennas. We cover one of the 2 antennas with different depths of soil, with different depths. At the same time, we measured the soil moisture using the probe. For example, we used 3 different probes to get the soil moisture, which covered this antenna. So then we get this result. This is a basic geometry and power relationships. So this is a test site in Beijing. We test from March to June in last year, and this is the soil covered the antenna. The antenna is underneath of the soil. This one is open sky. So then we pour water into the soil and know the true value of the soil moisture, and we measured the depth of the soil. So for each depth, we wait for the soil moisture from a high value to a low value, right? Then we collect and calculate the data from the video satellites, and of course we do the data processing for the GPS. So then we get this curve. So the conclusion is that the soil moisture, the soil depth is around 14 centimeters, 14 more or less 14 centimeters. Then we have no any signals from the antennas which was located underneath the soil. So that means the L-band signal could penetrate the soil in around 14 or 10 centimeters. So this is our test results in Mongolia in 2009. This test used the 2 antennas technique, which is not APT. So we used the HCP antenna to up to the direct signals, and we used the LHCP antennas to the ground. So then we pour water here. We do the data processing like this. This one here we pour water from this point. The time is 200 seconds. Then the reflected correlation will increase over the time. So this data is from the probe. Of course, there is some system difference. So the calibration is quite important for this soil moisture remote sensing applications. So another application configuration is the one antenna mode, but this one is different from the APT. It is similar as a PIT, but it's not PIT because it is used the geodesy network application. So the idea is about this. So the geodetic antenna can collect the data directly from the satellites and the multipass information from the reflected surface. So then the signal noise ratio signals will be written like this. The direct signals, the multipass signals, and the couple components like this. So then if we cancel this red line, we minus this red line, then we can get this, the right one. So from this data curve, we can calculate the frequency, the amplitude, and the phase information from this curve. Then all the different parameters could be used to calculate the soil moisture. So this is a test site in Beijing, Shandong in China, and this is a Valencia, Spain. So in Valencia, Spain test site, the two antennas configuration mode and the one antenna's configuration mode are tested together. So here you can see this is a different crops. This is wheat, right? This is wheat. This is crops. Yes, yeah. For the Beidou system test, we used different models to do. Firstly, we used dual frequency data. Of course, before dual frequency data were used, we used single frequency data. But the dual frequency data could give us a little bit better accuracy. So, for example, this is B1 and B2, the calculation result. So here, the blue column is the penetration, the rainfall meters. This is the rainfall meters. So you can see when there's a rain, then the soil moisture will be high. So after that, we integrate the data from more than one satellite. So multi-satellite, dual frequency. So of course, the accuracy has a little bit improvement. So this is some examples of our test. So for the GNSS-R polarization, I have explained more in the last class, and even this night, I explained a little on this polarization. So here, I will explain more on this polarization because the scattering is important for this. We all know the GNSS signals reflected from the Earth's surface, its waveform was distorted and polarization flipped. Of course, when the elevation angle is less than a value, the polarization will not flip. This is quite important. So even though in the real application scenario, we must think about method to reduce polarization loss and receive reflected signals efficiently. So different antennas were used for different receivers. For example, in the soil moisture experiment performed by United States, it used LHCP to receive reflected signals. As mentioned above, we also used the LHCP antenna to do the soil moisture experiment. So of course, for the APT technique, the linear polarization antennas were used. So in some experiment in United States, the linear and the circular polarization were all used in one experiment. So actually, a few years before, we also built some linear polarization antenna and do some initial test used this technique, but we didn't process more. So we have not published some results on this technique. But anyway, this is quite important for us. Maybe all of you in Arab countries or Jordan centers, our colleagues can work on this area to test the soil moisture surroundings. So a young scientist from China, Ms. Wu, investigate the reflected signals polarization properties in microwave radiative transfer model. Assume that the transmitted signals are RHCP, the polarizations of R to R, R to L, R to H, R to V. So this is a different transform mode. So she simulated the different scenario. So from her simulations, it can be seen that as for RL polarization, scattering values only exist at larger incident angles. So dynamic ranges of linear polarization, both horizontal and vertical, were larger, and their scattering response exists at the whole incident angles. So even we have already know this trend, but this young scientist simulation give us some more information on the vegetation cover. So it's quite important for the soil moisture calculation. And in her simulation, there have information on the heat of the vegetation, the heat of the vegetation, which covers the soil. So it's quite important for the vegetation calculation. So for the roughness effect, it will have some different errors introduced by the different coherent or incoherent time. So it is because the first Fresnel zone and the glistening zone are different. So for the specular scattering coefficients of GNSS-R is increasing with the forest biomass increasing. So, so it's quite important to know these two different zones, the first Fresnel zone and the glistening zone, because the two different zones have different effects on the coherent time and the incoherent time. So this is the simulation from Ms. Wu. So we can say when the stem diameters are fixed, like this, the scattering coefficient sigma is different for RV and RL. So it's obvious. So this is the basic fundamentals to do the biomass or vegetation calculation. So here I show you the examples of the soil moisture monitoring site in the whole world. This is Spain, Valencia universities. Actually, we have a joint project and we test the soil moisture using our own BeiDou receiver from Chinese manufacturer and the equipment from European institutes. So this is the Colorado University soil moisture. It used the GNSS-R, so not APT. This is the geodetical antennas. So this is the University Polytechnic de Catalonia, so soil moisture calculation site. So this is a Toulouse, third Toulouse. So we have a joint project named Dragon Program, which are the joint program between the China and the Europe. So we applied one joint research program with this university. University. So the fourth one, I will quickly talk on the cryptospheric sensing using GNSS-R. Actually, GNSS-R could be used for the dry snow because the L-band signal could penetrate into dry snow down to 200 and 300 meters deep. Of course, the signals reflected of these smooth surfaces have longer coherence times. So the signals present interferometric fringes produced by the interference between reflections of different internal snow layers. So I will show you in the next slide, this one. So for the whole snow layers, different layers will have different reflections. So here, the reflected signals is accumulation of all these signals. Of course, if the antenna's beam is not wide enough to cover this zone, the power will lose. So I explained in the last class. So for this dry snow calculation, the model was called multiple ray single reflection. So multiple ray means the incidence path is more than 1, but the reflected path is only 1 to the receiver. So we used the observable lag hologram to describe these signals. So last time I just show you quick for these observables. So we called this observable as defined observable from the primary observable, which is a DM waveform or DDM waveform. So this is the experiment result from the Antarctic station. So here we can see the complex waveforms 1 second integration. So this is the synthesized complex waveform for all the Dopplers. So used the direct signal with no reflection is a reference field. So this technique will try to see the rest of possible contributing rays present in the data. So of course, this data include some information about atmosphere, surface, subsurface, and more. So this is for the wet snow monitoring. So the wet snow is a bit different from the dry snow. So we can look at the wet snow like soil. So then the test methodology is similar as the soil moisture test. However, the snow above the sea ice or the lake ice detection has some specific features to be considered. So this is the test site in China, in Xinjiang province, Arte. So this test site is from Chang'an University. So this slide is from my colleagues, not myself. So I didn't do any test for the snow. So this from ETH. So I worked together with ETH to do the soil moisture, but not the snow. So this snow test site is only done by ETH, the Professor Alan Eger. So we worked together to test the soil moisture in Beijing and Tongzhou. My first picture in the previous slides. And we have a dragging program in the fourth dragging program, and I applied the fifth dragging program with the Toulouse third university. So this is the sea ice monitoring. So of course, the sea ice is quite important for the maritime. So this is the idea. So we tested in Tianjin in 2014. So you can see the seawater, the polarization ratio is around 10, but for the sea ice, it's less than 2. So this is the basic idea for the test. So this is the antenna configuration. We have 2 antennas, but we used the value from the polarization ratio, not only one polarization. So this is very typical case study. So and also we used the satellite-based GNSS-R to detect the sea ice boundary. So the detection probability is quite good. It's more than 95%. So for the ice thickness, is another challenging topic for the remote sensing. So many remote sensing techniques are difficult to get this information. So we try to use the power ratio between the polarization component from the reflective signals to do the eyes thickness calculation. So we have a few initial results published in Chinese magazine and in our own monograph. So the fifth application in remote sensing is the oil slick. So you know the oil on the sea is a pollution. So we will not hope there will oil slick, but how to protect our sea water? So oil slick detection is quite important. So we test this scenario in the oil pond. So we pour oil into the pond and collect the data using this antenna. You can see antenna down looking to the pond. So this is the geometry of visible satellites. So this is the dielectric constant over the time, which means it changes with the oil content. So the more oil, then the less dielectric constant. So the last application is a new application area, which is biostatic SAR imagery. So we do some simulations. For example, this one is 5 object simulations for the imagery, and we test in Shandong, Dongying city when we do the sea level or sea roughness experiment. We collect the data in December to see the imaging to match the ship. So we collect the data from this antenna and get the imaging to match this ship. So for this application scenario, we used backward signals plus the forward signals. So before these slides, all of my slides are used forward signals, but for the imaging technique, backward signal and forward signals are used. So this is the GNSS-R SAR imaging from Italy. So from Italy. So this is the whole 6 typical remote application area. So as a conclusion, I have a few slides. So GNSS-R, what's the meaning of R? Reflections means R. Remote sensing is R. So if we say GNSS remote sensing, then it has a broader meaning than GNSS-R itself, because of our R is GNSS reflectometry, not the GNSS remote sensing all, because GNSS remote sensing includes the directional signal applications. So we use reflectometry. So reflectometry also R. So the antenna configuration mode, we can use 1 no problem. One geodetic antenna, one linear polarization antenna, or 1 plus 1, 1 RHCP plus 1 LHCP. 1 plus 2, 1 RHCP plus 1 RHCP and 1 LHCP. Of course, we can use 1 plus 3 antennas configuration. For example, 1 is RHCP and 1 is LHCP. Another 2 is linear polarization, vertical and horizontal. So I think it has many configurations. Of course, the theoretical study is also important, which includes the geometrical optics model and the physical optics model. Both models are important, and they will have different application scenario. So for our BDO system, we have special features like different orbits, GEO, MEO, and AGSO. For GNSS-R, GEO satellites has stable observed geometry to the Earth. So let's imagine if the receiver is static, the satellite is GEO, then the detection area is fixed. Thirdly, the GEO satellite signals has better performance, especially in the low latitude area because of the geometry. So these characteristics of GNSS has advantages in long-term and stable observations of earthquake-prone areas. Maybe in the future, this GNSS-R could be used for the earthquake detection and the flood-prone area and some other new applications area. So let's work together to find more applications. So that's all for my presentation. I hope to give you some new information. Thank you.
Dr. Yang, thank you very much for your very useful lecture. We have some questions in the chat. Please, we'll start with the last question, which is which software are used to analyze this data, and is it open source software?
No, at this moment we didn't have the open source code. All the software we used was developed by ourselves.
Yeah. Then we have a second question from Jasser Al-Abid.
Sorry?
We have another question from Jasser.
Jasser, okay.
Jasser, yeah. Just a minute, please, to take his question. This is question in the chat. Can you read the question in the chat?
So who is preparing the question?
Is okay. Is in principle is possible to establish a geoid model from those measurements or from this technology in general? And if yes, any ideas about the expected achievable accuracy?
You mean the modeling and the accuracy?
Yeah.
Yes.
Can you read model from this information?
Yes, yes. We, some of the modeling is from the open published papers. Some models was developed by ourselves,
Yeah.
For example, ZV model was published in the journal paper, but for the parameters selection in the ZV, we do some tests and confirmed some fixed value for some specific application site, and some models like the wind speed and the signal wave height model. We developed these two models by ourselves.
Professor Ala Al-Nahri from the Egyptian National Remote Sensing Authority. Please.
Do you hear me?
Yeah.
Yeah.
This is Ala Al-Nahri, a professor of remote sensing and GIS at the National Authority for Remote Sensing and Space Sciences of Egypt. First of all, I'd like to repeat my appreciations to Professor Dr. Aouni Basha Al-Khasawna, our leader in the regional center for teaching space sciences and technology, West Asia, for his contacting with the distinguished experts from the other regional centers all over the world. My question is, I'd like to appreciate Prof. Young. I'd like to ask about something. Your lecture handled many more topics. One of them, sea roughness, sea surface roughness, winds, and typhoons. Did you make any experiments about ice melting in the Arctic and Antarctic that led to sea level rise? And have you measured the melting rate at those oceans or not?
I understand your questions. For the ice, for the sea ice.
Ice melting rate.
Yes, I detected for 3 years, because in China the ice is only occur in winter, so only a few months. So I detected 3 times during 3 years, right? So, but the data is not much more. The data is not much more. So this is the first result. Secondly, for the ice melting, in my data, I can share all this data to all of you. We found the ice melting process. For example, during a few days, some time before, it's very cold. Then the ice is very thick. But some day later, the temperature is higher, so the ice is melting. So we found this this time, from ice to melting. But this calculation is post-processing. We collect the data to get home and then do the calculation. So for the modeling, at this moment, I myself, my research group has no, meter model to do this. For the Arctic, in the north of the Earth,
Yeah.
I didn't do the test. No.
And what's about melting rate, ice melting rate? And did you make a correlation between temperature and ice melting?
Not yet, because the melting rate needs much more data to do, So my data set is not more. Yes, yeah, but it's quite important.
Yeah.
They're very good questions. I will work more on this.
Thank you very much.
If you have interest, we can work together.
Yeah, I'm very interested in climate change and sea level rise and melting, and I did many more researches at that field.
Yeah, the boundary of ice, detection. We have performed this data processing using the satellite data. Yeah, we do this. Yes, we developed our own software to do this.
Yeah. Okay.
We have a question from PhD student, Niveen, from University, I think. Niveen? I think she has a problem with unmuting. Engineer Niveen?
أخ إبراهيم، أعتقد أنه الوقت الآن تأخر كثير. سامعني إبراهيم؟
نعم دكتور، معك.
إذا ما في أسئلة اسمح لي أن أنهي هذه المحاضرة القيمة. If there is no question, will you please allow me to end up this very important presentation, which is really, we are highly and sincerely gratitude to the Professor Yang, and also special thanks to the director of the Regional Center for Space Science Technology Education of Asian Pacific, my actually sincere friend, Dr. Wang, for this kind and distinguished cooperation, which is actually whatever we speak, we cannot express our feeling and the pleasure towards the kind of cooperation you are giving us. Let me truly appreciate from my heart and for the time you have given us, Dr. Yang.
Yes.
And also I have to also remind you about our nice Xian for his distinguished lectures and for their efforts which they have given to prepare these kind of and important of materials to actually give it to us. It is not easy actually to have these kind of materials easily for the students which we are looking. My colleague from Egypt, Dr. Osama Shalabiya, who is the actually Dean Faculty of Swayf, you see the navigation and satellite, he was actually asking me in a special letter that he needs such kind of, let me say, lectures, which may his students, they attend it and they get benefit of it. I am really very much appreciated, and I would like that also we will give more and more nice presentations for our actually students, for our doctors, which actually this kind of technology, we consider it is advanced in China. And thank you very much on behalf of all of my colleagues in Regional Center for Space Science and Technology for all those attendees, and emphasizing my also thankful to Behind University, particularly our regional center. And we have really enjoyed, on behalf of my colleagues, every minute of your presentation, as well as your marvelous sense of humor while you are giving us these lectures. Again, I would like to express my heart and warm love to all Chinese actually partner, and also Dr. Ala and others. Sorry not to mention them. Also, I have seen Dr. Ashraf Shakir, Dr. Mukarram, and many of my friends, they are attending from Egypt and from other countries. Thank you very much being with us. And again, my deepest sincere and friendship to my colleague and my friend, Professor Wang. Please, Mr. Wang, I just request you if you would like to express a few words by the end of this presentation and workshop, and we'll see you next time. We are actually now becoming very much fond to see your lectures, and thank you for everyone.
Okay, thank you, Dr. Oni. I have not much to say. So also, I think it's our pleasure to work with our partner, the UN Regional Center in Jordan. And I think this lecture will be helpful. And also, I think we can cooperate in extend it to other areas. If you have some requirements or demands, just let us know. We will try our best to work with our regional, our center in Jordan. We are always in your side.
Thank you. So kind of you. Looking forward to see you as soon as possible after we just finish from this COVID-19. And I hope that we are progressing well in Jordan as well in China.
Yeah. So
okay,
also looking forward to see you. Yeah.
Thank you very much. And yes, thank you. And I wish you all the best. And goodbye for everybody. Wassalamu alaikum wa rahmatullahi wa barakatuh.
Thank you.
Bye-bye.
Thank you.